Some ideas regarding memory abstraction. Memory issues in the early x86 processors. It was hard to access all large addresses. Why is that? It was because registers was small, so it was hard to represent large addresses. For example, if you had much memory, it was very hard for your program to use all that memory, because in order to represent the location in memory that you wanted, you have to do some very strange tricks with your registers. I remind you that, for example, a 16-bit register only allows you to access 2 to the power of 16 bytes, which is only 64 kilobytes. It used to be a lot in the old days, but these days it is not enough. Even in the days of the 16-bit registers, at some point people figured out that it is just not enough, and many programs had to do lots of strange memory tricks to be able to access large addresses. It was pretty hard to do it. Another issue that made programming pretty hard in those days was that programs could actually corrupt each other's memory. For example, maybe there are two different programs that run on the operation system, and one program uses some part of the memory. The other program could just overwrite the first program's memory, and that would cause a problem. Therefore, two solutions to this problem were introduced in the future. And those two solutions were segmentation, which was introduced in the 8086 model of the Intel processor. And it was mostly about using two registers to represent one longer address. If you have ever opened some kind of an old assembly book, you've probably seen it. It was very common in the past to use this method of using two registers to represent one longer address. It used to be using two 16-bit registers to create one 20-bit address. And it was pretty strange. One address could be represented in many ways, for example. Some later idea, which came with the 8386 Intel processor model, was paging. Paging solved most of the problem that the end programmers had with memory. After the introduction of paging, the programmer didn't have to deal with all the memory management. It was done for him by the operation system. Some points about paging. Paging allows to simulate a lot of memory, even when actually there is only a little. And also, every program thinks that it owns all the memory in the system. Another advantage was that programs could not override each other's memory. It provides some kind of isolation in memory. It also handles privilege levels for security. What does it mean? It means that some parts of the memory are more privileged than other parts of the memory, which means that if you are not a very privileged user, for example, in the system, or maybe not a very privileged program, then you cannot write some parts of the memory, or maybe not read them. The paging experience as a whole is created by cooperation between the operation system and the processor. So the processor provides some kind of hardware support for this paging idea, but much of it has to be implemented inside the operation system. For example, I use Windows here. The Windows operation system has a whole chunk of code that deals with the whole paging idea. If you were worried, I want to tell you some cheerful words. Today, the end programmer, which is actually you, doesn't have to worry about memory management. And why is that? Your program will run under the illusion of owning lots of flat memory, which means that if I didn't tell you about this paging idea, I promise you that you would probably not felt it yourself, because there is a very good abstraction. Your program will think that everything is as usual. It will run and it will think that you have a very large chunk of flat memory, and it will also think that it owns all the memory. it will not know about the existence of other programs. However, in reality, your program does share the total memory of the system with other programs. The operation system and the processor work together to create this illusion of flat memory. Another important idea is that the memory addresses that your program sees are not the real addresses. For example, your program might think that some cell is represented by some kind of address. However, it is not the physical address. It is not the address that is used to refer to this cell in the actual RAM, in the actual physical memory. This kind of not real memory or not real addresses are called virtual. I want to show some kind of illustration. We are not really going to see practical paging operation system code because we are not really going to deal with it. It is a pretty advanced subject, but I just want to make sure that you understand that the memory which your program accesses is mostly virtual and the addresses are virtual. It is not the real physical memory. For example, let's look at two programs. Maybe those are two programs that you have written yourself, and then you run them at the same time. Also assume that those programs have some memory usage. For example, this is the memory map of program A, and this is the memory map of program B. This is the RAM card, the RAM stick, which resides in your computer, for example. The operation system is going to divide the memory chunks so that program A and program B both will have the experience of flat, contiguous memory. However, in reality, the memory is not contiguous or flat. For example, this part of program A's memory is actually located here on the RAM, and the other part is located here. So for example, maybe there is some cell here in the beginning, and program A might think that it has some address. However, this address is not the real address. This is the real address here. At the same time, program B's memory is also on the RAM stick. However, it is on different locations. Both program A and program B have the illusion of owning all the memory. Program A thinks that it owns all the memory, and also it thinks that the memory is flat. And B thinks the same. However, it is not true. The operation system and the processor work together using the paging mechanism to create this illusion. And I even want to go further in what is possible using this illusion. Let's think about, for example, the case where program A and program B use really lots of memory, and there is not enough memory on the RAM stick. Recent operation systems have the ability of swapping, which is known as putting some of the memory inside the hard disk instead of the RAM. Why would someone want to do this? Usually, RAM is more expensive than hard disk memory. For example, in my computer I have 1 terabyte of hard disk memory and only 4 gigabytes of RAM memory. So obviously I have more space inside my hard disk. Space is not really an issue regarding hard disk. But when talking about RAM, sometimes you don't have enough RAM if you open lots of programs in your computer. In this case, the operation system is going to do the following. It will say that it doesn't have enough room on the RAM, so it is going to put some of the memory chunks inside the hard disk. And only when your program is going to access this part, it will be reloaded back to the RAM, and some other part of the program will be stored back in the hard disk. The operation system actually swaps chunks of memory to make sure that your program has the perfect experience of flat contiguous memory, although it actually doesn't. Program A thinks that the system has lots of memory, but the truth is that the system doesn't have so much memory. The memory is just swapped to the hard disk from time to time. This kind of swapping usually cost in running performance. Usually when these kind of things happen, you will feel it in the performance of your program. The program will become a bit slower for a moment because part of the memory is taken from the hard disk and loaded to the RAM, and this process takes some time. Some people say that when you use the computer and you feel some kind of a slow moment, it usually happens because of swapping, because of moving memory from the hard disk to the RAM and back. Summary of the abstract ideas that we have learned so far. Some tasks require that our programs will be able to remember more data. We've seen it with the first example of sorting numbers in some kind of a large array. There are hardware devices that store big amounts of data, and this is opposed to the processor, which only has a few registers. These hardware devices are separate from the processor, and the processor can communicate with the memory devices using memory-related instructions. Those kind of instructions are something that we are going to learn about in the very near future. Your programs are given the illusion of flat memory. This boils down to contiguous address space, unique ownership of memory, and also the illusion of lots of memory. All this kind of illusion using the paging mechanism, which is relatively pretty recent. It is pretty new in the world of programming. It gives you the freedom to think about your code instead of always thinking about memory management. And it is very liberating. So you are very lucky to live in this time, where you don't have to represent addresses using lots of registers and do some kind of strange tricks yourself. You can just access the memory as you wish, and the operation system and the processor are going to do all the work of managing the memory for you. Some other words. This lesson was kind of abstract. We didn't see any real code, and there was lots of hand waving about the subject of memory. And that is because it might look simple at the first sight. However, the internal memory management is usually a very complex thing. And I don't want to deal with it at this point of the course. This is a beginner course. So if you are not going to write an operation system yourself or a BIOS or something like that, you really don't have to know much about the memory management. You only have to know about it in some kind of abstract way. So when you run two programs, you can understand what happens. If you didn't know about this paging mechanism, you might, for example, run two programs and then try to access the same location in memory and expect that the data will move from one program to another. But this cannot happen because of the isolation that the paging mechanism gives. This is about what I wanted to tell you today. See you next time.